In this video, we're solving a static equilibrium problem with a heavy horizontal beam suspended from two vertical cables. And the complication in this problem is that we have a person walking along the heavy beam from the left end to the right end. Their current position is described as X. And as they walk from the left to the right, the tensions in those two cables continuously change. So the goal of the problem in parts A and B is to get the tension in each of those cables as a function of X. And then in part C, just to verify that our answers are correct, we look at the sum of those two tensions and prove that it's equal to the sum of the weights of the two masses in the problem, guaranteeing that the forces in the y direction balance. So we start by getting force vectors into the diagram. And we have four forces going on. Remember that gravity acts at the center of mass of the heavy beam. So that's going to be a force of capital M times G. The person's mass is labeled as lowercase m. So we have a force of little mg located at a distance of x from the left end of the beam. And then we have our tensions in the cables, T1 of x on the left side and T2 of x on the right side. Again, those are written as functions of x because they continuously change as the person walks along the beam. And in part A, we want the tension in the left cable as a function of x. And my intention when I wrote this problem is that students would use a torque analysis around the right end of the beam. I can call that rotation axis number 2 since T2 is attached to it. The point of that is that T2 produces no torque with respect to that axis because the lever arm is 0. So the only torques being exerted with respect to rotation axis 2 are caused by the weights of the person and the beam, and then T1 out there at a distance of 3 meters from the rotation axis. Now, one of the first things I notice here is to get the lever arm for the weight of the person, I need to know the distance from the person to the right end of the beam. Well, the beam is 3 meters long, and the person has moved a distance of x from the left end. So that means the person is a distance of 3 minus x from the right end. So we get to work balancing the torques with respect to rotation axis 2. And just kind of informally here, what we're saying is the sum of all the clockwise torques better be equal to the sum of all the counterclockwise torques. Well, the only clockwise torque with respect to the right end of the beam is caused by T1. So I have T1 of x. Remember, that is not saying T1 multiplied by x. It's just highlighting the function notation because T1 depends on x. That force has a lever arm of 3 meters. So T1 of x times 3 is equal to the sum of the counterclockwise torques. And here I have mg, the weight of the person, at a distance of 3 minus x from the rotation axis. And then the weight of the beam, capital Mg, times its lever arm, and that's located at the center of this uniform beam, which is 1.5 meters from the edge. So we can plug in our numbers and find T1 as a function of x. So we plugged into the mass of the person, that was 75 kilograms. The mass of the beam, 177 kilograms. We're using 9.8 as an approximation for G. And when we collect all the constants in that expression, we get 1602. The units on that is newtons, and then minus 245x. Now to tackle part B, getting the tension in the right cable as a function of x, we just use the left end as our rotation axis, and I'll call that rotation axis 1. And again, the point there is that the torque exerted by T1 with respect to that axis is 0 because the lever arm is 0. So we get into balancing our torques again. And this time the clockwise torques are caused by the weights of the person and the beam. I have the weight of the person times the lever arm there, which is now simply x, plus the weight of the beam, capital Mg, times its lever arm, again 1.5 meters. And that better be equal to the counterclockwise torque exerted by T2. So I have T2 of x times its lever arm, which is the full 3 meters. So again, we quickly solve for T2 of x, and we put the numbers in. And when we combine all of our like terms this time, we get 245x plus 867 newtons. Finally, we can verify that we've got the correct answers by showing that no matter what the value of x is, the two tensions, those two upward forces, are always going to add up to the same total force as both weights combined. In other words, we're showing that the net force in the y direction is always 0 regardless of what x is. So first we can compute T1 of x plus T2 of x. And we get a total of about 2,470 newtons. Notice that the x-containing terms perfectly canceled out here. So we're able to say the sum of those two tensions is always about 2,470 newtons. Next, we compute the total weight of the person plus the beam, and that gives us our total downward force on the system. And again, to 3 significant digits, this rounds to 2,470 newtons. So yeah, our total upward force is T1 plus T2, and that gives us the same number as the total downward force, a result that's independent of the position of the person. So we're confident we've got the right answers in part A and B. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.